Welcome to Calculus. Today we will investigate how to tell if a function is differentiable at a certain value x equals c, focusing on the definition of the derivative to compare right and left-hand limits of the average rate of change. Let's investigate differentiability in terms of how it compares to continuity of a function, and we'll do this through a flow chart. And in fact, what we'll start with is a theorem. So let's pick up this theorem that connects continuity with differentiability. And the way this theorem goes is if a function is differentiable at a certain x equals c, and that's our hypothesis to the theorem. The conclusion is this: then the function is continuous at that same x equals c. So we can see that there's definitely a connection between differentiability and continuity at a certain x value. And what really interests us is another way of writing this same statement. So if we think that this is some hypothesis P implies some conclusion Q, really where we want to focus in terms of our work today is the contrapositive, which is not Q implies not P. So remember that those are equivalent. The original if-then statement is the same as its contrapositive. So let's write out what the contrapositive would be. So we're going to contradict the conclusion. So if a function is not continuous, so that's not Q, then, and we'll say at x equals c, then the function is not differentiable at x equals c. Now, we need to focus then on how we can apply this to certain functions. And let's take a look at this consideration in a flow chart. So let's just consider that we've got a given function. Let's just put it there. There's our function. And there's two possibilities in terms of its continuity. So say, for instance, that function is discontinuous at x equals c. What we can conclude then is by this statement here in red, the contrapositive of our original theorem, our conclusion is that function is also not differentiable. So therefore, not differentiable at x equals c. So that's one case. So if we know that a function's not continuous at a certain x value, the conclusion we can make is that it's also not differentiable at that same x value. So let's consider the other possibility. Let's say that it is continuous at x equals c. So then at that point, we do again have two different options in terms of differentiability. So it could be that function is in fact differentiable. Where we want to focus today is right there at that differentiable case, x equals c, and also at the possibility that a function could be continuous and not differentiable. So really we need to kind of fill in this case here. What are those functions and what's their qualities that makes them continuous at a certain value but not differentiable at that same place? So where we're going to fill in terms of our flow chart is right here in the light blue, a function that is continuous at x equals c, but not differentiable at that same place. And we want to take a look at three different possibilities. So the first possibility is that what we'll see when we take the limit from the left and compare it to the limit from the right of the instantaneous rate of change, which again is our definition of the derivative, that those are not equal. So let's write that kind of in a shorthand here. So that first case would be that the limit as x approaches c from the left of the difference of the instantaneous rate of change f of x minus f of c over x minus c, if that does not equal the limit, and we'll just switch colors here so we can note there are two separate directions. The limit as x approaches c from the right of the same average rate of change expression, f of x minus f of c over x minus c. Now let's just see an example. So an example of this situation is the parent function for absolute value functions. So f of x equals absolute value of x at x equals 0. And let's just take a look at the graph, because really this example is best viewed graphically. So if I put the plane there and graphed absolute value, that's that characteristic V shape. So if I look here at the tangent line as x approaches 0 from the left. So I'm going to put this in shorthand. The tangent line as x approaches 0 from the left, the slope of that left-hand side is -1. When I compare that to the slope of the tangent line as x approaches 0 from the right, I can see that the slope of that right-hand side is a constant +1. And because -1 does not equal +1, by this first case, we could say that that function is not differentiable at x equals 0. And we give a name to this type of function at that particular juncture there. We call that a corner. So that's one case. At a certain x value, if a function has a different left-hand limit of the instantaneous rate of change compared to the right-hand limit, we say that it's not differentiable at that x value. It is a corner. So let's also consider a second possibility. Could be that we have some kind of function where both directions, so if I take the limit of the difference quotient, limit of the average rate of change from the left, so f prime of c from the left, if that's the same as f prime of c from the right, and they're both positive infinity, or those two limits of the average rate of change from the left and from the right are both equal, and they have a value of -infinity, what we would say there is that we have a vertical, or in other words, undefined slope tangent line at x equals c. And that, if we think about an example, would look something like this. So let's say here that we've got the parent function for the cube roots. So f of x equals the cube root of x. And again, at x equals 0 is where we're going to focus our attention for this example. Graphically, if I consider here the cube root function, so recall how that begins in quadrant 3 and then turns sharply. That's what's really important. It turns almost perpendicular and then continues into quadrant 1. At x equals 0, we've got tangent lines that have positive slope that at 0 become a vertical tangent line, and the slope of that tangent line is undefined. And in that case, what we would say is that's an instance of this second situation where the left-hand limit equals the right-hand limit of the average rate of change, but it equals infinity, or in other cases, negative infinity, not differentiable. So if we were to describe this, and we call that first one a corner, this second case is a vertical tangent line. Well, let's consider a third and final case here and see if you can predict the qualities of that one. So again, what I could have is that potentially I've got the limit of the average rate of change from the left equals positive infinity, and the limit from the right equals negative infinity. So it's related to our second case, but notice one's positive infinity, one's negative infinity, or vice versa. Could be that the limit of the average rate of change from the left equals negative infinity, and the limit of the average rate of change from the right equals positive infinity. So notice how it's different from our second case. In this instance, we've got a vertical tangent line, but from the left, it's got a negative slope that's becoming vertical. From the right, it's becoming, or positive slope becoming vertical, or vice versa. Again, a picture is worth 1,000 equations. So let's look at an example. Here, a good example is the rational exponent equation, f of x equals x to the power of 2/3. And it's got really a situation that kind of combines what we see in those first two cases. So here, if we graph this one, just to take a look at that function, it really is very symmetric. It's an even function around the y-axis there, so it's reflective symmetry in the y-axis. And what we see is that definitely that tangent line at 0, so I should specify it's at x equals 0. At 0, our tangent line again is vertical, but the difference in the limits from the left and the right, the limit from the left, if I think about how that left-hand side would approach the vertical asymptote, it would have a negative slope. I'll say it's a negative m. Whereas from the right-hand side, if I characterize that as it approaches that vertical tangent line, its slope would be positive. And so we see this instance. In this case, what we're seeing is this second scenario. That again is not differentiable. We give a name to that one. That one's called a cusp. So again, just to recap there, our flow chart starts with a function. It could be continuous, it could be discontinuous. If it's discontinuous, it's not differentiable at that x value. If it is continuous at that x value, it could be differentiable. It might not be differentiable if it falls into one of these three cases. If it has a corner where the left-hand limit of the average rate of change doesn't equal the right-hand limit of the average rate of change, could have a vertical tangent line to where from both sides we approach the same infinity or negative infinity, or it could have a cusp, which means it shows opposite sign infinity from the left and from the right. Well, those are our three kind of cases for continuous functions that are not differentiable. Let's take a look at three examples. So we'll scroll down to number 1 here. So here we want to determine whether the function has a derivative at c. If it does, what is the derivative? And if it does not, give the reason why. So here we're looking at kind of a relative to that. In fact, that is the same x to the power of 2/3, but different from looking at it at x equals 0, we're now considering that our c value or our x value is at -8. So we do want to just consider if that function is continuous at -8. So remember our 3 criteria for continuity. The first criteria, again, so if, let's start that. So if a function is, if we have a function f of x defined on a closed interval that shows these 3 properties. So the first one is that at that certain x value, f at c is defined. So on the actual function, if I have f at -8, so we'll check that in a moment. Secondly, if the limit as x approaches c of f of x exists. And thirdly, if the value f of c equals the limit as x approaches c for the function, then we conclude the function is continuous. Then f of x is continuous at x equals c. So again, that's our definition for continuity, those 3 criteria. So let's just take a look at this function. We'll graph it on Desmos. So I'm going to head over to that calculator just to check the continuity. And again, it's the parent function for the rational exponent 2/3. So f of x equals x to the power of 2/3. And what we're interested in is this value at 8. So what we want to say is, okay, if I were to create this value of the function at 8, and I can check this here on Desmos just by tracing, that first criteria says that it should be defined at -8. So if I can center that point at -8, definitely what the calculator is showing us is that the value of the function at -8 is 4. When we look at our second criteria, we need to say, does a limit exist of the function at -8? And we can see just without rigorous algebraic manipulation, we can see from the graph that the left-hand side of that function as it approaches -8 is 4. It's also 4 as we approach from the right-hand side. So definitely the limit exists at -8. And in fact, those are the same values. F at -8 equals the limit of f of x as x approaches -8. So kind of in an informal way here, we can confirm it is continuous here using the graphing calculator. Well, let's then try to find what is the limit, and we'll do this analytically. So let's set up our limit of the average rate of change. So I want to define some things here first. So I've got f of x, that's x to the power of 2/3. C is -8. X is x. And f at c, which is f at -8, is equal to -8 in parentheses raised to the power of 2/3. So I do want to evaluate that and get a single value. So remember, when I have a rational exponent, the denominator is a root. So the cube root of -8 is -2. So this becomes -2 to the power of 2. And -2 times -2 is 4. So that's my f at c is 4. So what we want to do then is set this limit of the average rate of change up. So it's the limit as x approaches that -8 value of, let's give the, well, we'll fill it in. So f of x is x to the power of 2/3. f at c we saw is 4, so minus 4. And then our x value is x. And we're going to subtract c is negative 8. Just to remind, for that limit of the average rate of change, it's the limit as x approaches c of f of x minus f of c over x minus c. So all we've done is taken that definition of the derivative in red and substituted in f of x, f of c, x, and c. So now I want to see if I can actually calculate the limit. So remember, if I tried direct substitution here, what I would end up with by plugging in negative 8 is 0 over 0. That's indeterminate. So I can just sense right now that I need to do some algebraic factoring. So what I'm going to do is I'm going to simplify here and then see if I can factor the numerator to cancel with some of the denominator. So that's the limit as x approaches negative 8 of a numerator. So what I'm seeing here is that this is really the difference of two squares. I can think x to the power of 2/3 is x to the power of 1/3 squared, and 4 is 2 squared. So using that idea, and it's a little unusual to be thinking about rational exponents there, but we can still apply the pattern. So the numerator would factor as x to the power of 1/3 plus 2 times x to the power of 1/3 minus 2. Again, just applying the difference of two squares pattern. Similarly, for my denominator, what I can say here is the minus minus is going to turn into a plus. And then, like we saw for my numerator, I could consider that this is the sum of two cubes. Let's make a case for that. So I could say that this is x to the power of 1/3 cubed. So that really has the value of just x. And then the cube root of 8 is 2, so 2 to the power of 3. So I could factor my denominator using the sum of two cubes pattern. So remember from algebra 2, that's for the sum, it's the first term under the cube, so x to the power of the cube root plus the 2. And then in parentheses, we have a trinomial, recall, and it's a quadratic. So this is x to the 1/3 squared, so that x to the power of 2/3. Then we have the minus sign next, so minus 2x to the power of 1/3 and plus that 2 squared, so that's 4. So we applied difference of two squares pattern to numerator to factor, sum of two cubes to factor the denominator. Why did we do that? I have two terms that are identical. X to the power of 1/3 plus 2 above and below, we can cancel. And when I do that, that allows me to apply direct substitution now. So this is now the limit as x approaches negative 8. All that's left in my numerator is x to the 3rd minus 2. And in denominator, x to the power of 2/3 minus 2x to the power of 1/3 plus 4. So I think we're okay to use direct substitution. So we'll switch over to a different color here, drop the limit notation, substitute in negative 8 for x. So negative 8 to the power of 1/3 minus 2 over negative 8 to the power of 2/3 minus 2 times negative 8 to the power of 1/3 plus 4. And now we just need to simplify that expression. So recall the power of 1/3 is equivalent to the cube root. So the cube root of negative 8 is negative 2 minus 2. So for my numerator, I can simplify, that's negative 4. And then in denominator, negative 8 to the power of 2/3, take the cube root first. So cube root of negative 8 is negative 2, and then square that for my numerator 2. That's positive 4. And then again, in that second term, negative 2 times parentheses negative 8, close parentheses power of 1/3. The negative 8 to the power of 1/3 is the cube root of negative 8. That's negative 2 times the coefficient negative 2 is another 4. So 4 plus 4 plus 4. And that adds up to 12. And then if I reduce that fraction, I have negative 1/3. And that is the value of the derivative at x equals negative 8. Again, we could interpret that as slope. The slope of the tangent line to that curve at negative 8 is negative 1/3. So just to kind of picture what that's doing, just remember from our continuity check, this function looks like this. So definitely at 0, it's got a cusp. But over here at negative 8, if I go up to the curve, pick a color here that would match that negative 1/3. If I drew in a tangent line there, the slope of the tangent line would be negative 1/3. And that looks about right. It's definitely a negative slope, and it's fairly flat, which is consistent with the value of 1/3. So definitely we could have the possibility that a function is continuous and differentiable, and number 1 shows that quality. Let's consider a second example. So this is number 3. And our task again is the same. We want to determine whether the function f has a derivative at c. If it does, what is the value of the derivative? In other words, what's the slope of the tangent line at that x value? And if it doesn't, we need to give the reason why. So here we've got the function f of x equals absolute value of x squared minus 4 at c equals 2. So let's just set up our limit of the average rate of change and see how that compares from the left and from the right. So let's set it up. So we'll consider here, first of all, that f at c is plugging in 2 for x. So just to calculate that out, that's 2 squared minus 4 with an absolute value. 2 squared minus 4 is 0. Absolute value of 0 is 0. So it turns out f at c has the value of 0. C itself is 2. So when we go to set up our limit of our average rate of change fraction, let's put it in general terms first. So limit as x approaches c of f of x minus f at c over x minus c. We'll fill in with our values. So our values are going to be the limit as x approaches 2 of f of x, so that's the absolute value of x squared minus 4 minus f at c, which is 0, over x minus 2. So what we want to do is simplify this first. And then we want to take a look at what's happening to the limit as we approach from the left compared to as we approach from the right. So here I've got limit as x approaches 2. Before we split into the two directions, we'll just do a simplification. So I can factor this x squared minus 4 in the difference of two squares pattern. That would be x minus 2 over times x plus 2 all over x minus 2. So I see a cancellation that can cancel through the absolute value bars. So x minus 2 cancels there. So as we get ready to look at the limit from the left and the right and compare them, we'll do so with this simpler limit. The limit as x approaches 2 of the absolute value of x plus 2. Now, I do want to keep in view this version. because I need to consider what's happening to this value as I approach from the left in contrast with what happens as I approach from the right. Since again, the absolute value is going to change all the signs to positive. So I kind of need to keep in view what is the sign of the denominator. So let's then compare the left hand with the right. So although I know that I've got this simplified form, I am going to kind of use the previous step when I look at these two sides. So from the left, let's consider the limit as x approaches positive 2 from the left. And I will write that previous step. So absolute value x minus 2, x plus 2 over x minus 2. And what I want to consider is kind of an analytical approach, because I know if I plug in 2 there, I'm going to get an indeterminate form, 0 over 0. But if I consider, okay, what's happening to this denominator if I were to plug in a number to the left of 2, so a number that's slightly smaller than 2. So let's just say that's 1.999. So what I'll see when I plug this in is I know that this numerator is going to be a positive number, some magnitude, I'm not quite sure. The denominator is going to be a positive, well, let me back up. If I put 1.999 minus 2, it's not going to be positive. It will be a negative small number. And so what I see there is that as I evaluate this limit from the left, is that the sign is going to be negative. Now, I can go ahead and calculate the limit. Just kind of keeping in mind from this form here, the simplified one, from the left, it will have a negative down below. So I just need to consider what sign this denominator is going to take. So my next step here would be to cancel this, but to keep in mind that this value would be negative. So I'm going to take that simplified form, the limit as x approaches 2 from the left, and I'm going to leave that negative sign out front. It's the negative absolute value x plus 2. So then I can apply direct substitution. Negative absolute value 2 plus 2 is negative absolute value 4, which is negative 4. Let's compare that then to the right-hand approach. So from the right hand, we'll take the limit as x approaches 2 from the right. And again, when I record the uncanceled version, so absolute value x minus 2 times x plus 2, I know that there will be a cancellation, but I want to consider what the sign of this denominator will be when I approach from the right. So in that case, this number would be slightly bigger than 2, something like 2.001. And so the sign on this denominator would have been positive as I approach 2 from the right. So again, just to kind of consider that the numerator is in absolute value, so it will be a positive number. And down below will be a positive small number. But again, the magnitude doesn't matter. What we're interested in is the sign. Positive divided by positive is positive. So in this case, the limit as x approaches 2 from the right of the simplified form is going to be positive absolute value. Let those cancel. X plus 2. Direct substitution would say that that's positive absolute value 2 plus 2, which is positive absolute value 4, which is positive 4. So when I compare those left and right sides, they're different. Let's check on the graph to make sure that that corresponds with what we're seeing on the graph at the x value of 2. So we'll show the view on Desmos here. And enter that function. So f of x equals absolute value of x squared minus 4. And just like we had seen, when I look at positive 2, as I approach from the left, the slope of the tangent line is definitely negative there. In fact, if we were to write an equation, I know the tangent line would go through the point 2, 0. So the equation of the tangent line from the left would be y equals negative 4x plus 8. So there I can see that's definitely a tangent line. It's just intersecting the graph at that one point, and it's the slope there is negative 4. And if I consider the other side as I approach from the right, y equals, in this case, 4x minus 8. Again, that's a good tangent line at that point, but its slope is opposite. So this one definitely we can approach analytically and then confirm here on the graph the left-hand limit of the average rate of change does not equal the right-hand limit of the average rate of change. And when we consider, if we go back to our 3 scenarios, whether this is a corner, a vertical tangent line, or a cusp, that really matches with what we had called a corner. It's similar to the absolute value function there. The left-hand side, the limit of the average rate of change does not equal the limit of the average change of rate of change from the right. So what we'll conclude here for number 3 is, if we were to write it out, the derivative of this function f of x at 2 does not exist. And if we were to make a case, what we could say is because the limit of the average rate of change, in other words, we could kind of shorthand here, the limit of the average rate of change at 2 from the left equals negative 4, which does not equal the limit of the average rate of change at 2 from the right, which is positive 4. Basically, we're saying that the left-hand and the right-hand limits of the average rate of change are not the same from the left or from the right. And that concludes that question. So there is an instance of a corner. And graphically, we can just kind of see it. We looked at the graph a moment ago. This function shows kind of an interesting behavior. It's like a parabola, but because it's absolute value, everything that would have been under the x-axis has been reflected up. And in fact, that's not the only corner here on this function. We definitely have a corner at x equals 2, also at x equals negative 2. So even though a function is continuous, it may not be differentiable. Let's see one final example. So here I've got a piecewise function. And again, my question is the same. Is it differentiable at a certain value of x equals c? So here we're looking at c equals 1/2. So we should consider, first of all, is it continuous? And I think the best way for us to do this one is just to look at a graph. So I'm going to head over to Desmos and just check and see, and we'll consider our 3 criteria for continuity from the Desmos graph. So I'm going to clear out our O function there. And recall to put a piecewise in Desmos, you want to do that two separate functions, and we'll just limit the domain. So the first part is -4 plus 2x. That's linear. And we're going to limit that to where x is less than or equal to half. So you can see that line showing up, and it terminates there at half, and it looks about the y value of -3. The other part of the piecewise function we'll call g of x, and that again is 4x squared plus 8. And that one we want to limit to x is, I'm typing that wrong, it's -4. And here I want to limit to x is greater than or equal to half. So let's just check continuity to begin. So the first question is, does f at c have a defined value? So our c value is half, and if I look here at the function, definitely it's defined. It's -3. So then the second criteria is, does the limit of, as x approaches half, of this function exist? So when I look from the left and from the right, both sides are approaching -3 from the left and from the right. So the limit exists and it equals -3. And then the third criteria is just that that value of the function equals the limit as x approaches that value of the function. And again, -3 equals -3. So definitely the function is continuous. Well, that bumps us into either differentiable or non-differentiable, and we got to consider, is this one of our special cases, or is it differentiable? So we'll go back to our notes screen, and what we need to do is set up our left hand and right hand limits of the average rate of change. So we'll start with the left approach, and that's going to be this first linear part. So we'll set this up. Again, what we're filling in is the limit as x approaches c of f of x minus f of c all over x minus c. Let me fix that. So for the left side, let's define f of x is going to be the original, -4 plus 2x. X itself is just x. And then we'll call f at c. See here, if I were to define that, I'm writing all kinds of mistakes here. Let me fix that. X is x. C is 1/2. So I'm calculating f at half. So I'm going to plug that in. It's -4 plus 2 times half. Then I just want to simplify that expression. -4, 2 times 1/2 is 1, so plus 1 has the value of -3. So I'm ready to set up that left-hand limit. So this is the limit as x approaches 1/2 from the left of numerator -4 plus 2x minus f of c is -3, so I'll double that negative, and that's all over x minus my c value, which is half. So that's the setup from the left-hand side. I want to simplify that limit now. So that's equal to the limit as x approaches 1/2 from the left. In my numerator, I can let these parentheses go, and then I'm going to call minus -3 plus 3. So the way that that would simplify, if I switch stuff around, is 2x, and then -4 plus 3 is -1, all over x minus 1/2. So I do see direct substitution would give the indeterminate form 0 over 0. So I want to see if I can factor that numerator to cancel with the denominator. So that equals, we'll stack vertically here. the limit as x approaches half from the left. And I see that I have a 2 that I could factor out of both terms. When I do that, I end up with 2x divided by 2 is just x, and then 1 divided by 2 is 1/2. And that reveals a nice cancellation of the binomial x minus half. And that is now ready to evaluate by direct substitution. The limit as x approaches 1/2 from the left of just 2 is 2. Let's compare that then to the limit of the function from the right at 1/2. So I'm going to set that one up. From the right, that's the second part of our piecewise function, which is 4x squared minus 4. So again, x is x. And then f at c is again f at 1/2. Let me just say that here, c is half. So that's going to be 4 times 1/2 in parentheses squared minus 4. So we'll simplify that. That's 4 times half squared is 1/4 minus 4. 4 times 1/4 is 1 minus 4 is -3. So again, we have the same value there at half. And we saw that on our graph. It ensures that our function is continuous. So let's set up our limit of the average rate of change. We'll use that red template up there. So here we'll be calculating the limit as x approaches 1/2 from the right. And we'll just plug in like we had created this. So my original function is 4x squared minus 4. And we're going to subtract from that the c value, or I'm sorry, our f at c value, which again is -3. And that's over x minus 1/2. That's our c. So just like we'd set up the left-hand approach, we've set up our right-hand approach. Now we need to simplify. So this equals the limit as x approaches 1/2 from the right. In my numerator, again, I can let those parentheses vanish, and we'll call minus -3 plus 3. So the way that this combines is as a numerator of 4x squared. -4 plus 3 is -1, and that's all over x minus half. So again, I want to factor out a 4 there. So my next step would look like the limit as x approaches 1/2 from the right. In my numerator, 4 times x squared minus 1 divided by 4 is 1/4. All over x minus half. And I see now that I can factor this quadratic as the difference of 2 squared. I just need to think that 1/4 is 1/2 squared. So I'll put this over here on the side just so we can consider this is the difference of 2 squares. X squared minus 1/4 is the same as x squared minus 1/2 squared. So I'm going to factor. This is the limit as x approaches half from the right of 4 times, that would factor as x plus 1/2 times x minus 1/2 all over x minus 1/2. So then we see the cancellation very clearly. And that sets us up for direct substitution. So again, I'm going to write that simplified version, get ready to substitute half for x. So all that's left here is 4 times x plus 1/2. So now I'm going to direct substitute. We'll change the color to say this is a transition to that direct substitution. So it's 4, instead of x, I'll write half plus half. And that's going to be half plus half is 1, so that's 4 times 1, which is 4. So now we have a chance to compare our left-hand limit of the average rate of change with the right-hand limit of the average rate of change. When I see that the left hand is equal to 2, the right hand is equal to 4, what can we conclude? Let's write it out. So the limit, in fact, what we'll do is shorthand. The derivative of this function at 1/2 from the left equals 2, which does not equal the limit of the average rate of change of the function at half from the right, which is 4. And so what we see here is, although this is a less sharp corner, this is not differentiable in the same reason that our absolute value of x squared minus 4 was not differentiable. It's got different limits, different slopes of the tangent lines on the left and the right. So what we'll say is f of x is not differentiable at x equals 1/2 because the limits of the average rate of change let me give myself some room here, are different from the left and the right. So that offers some justification for our classification of this function as continuous but not differentiable. And that we want to just circle or box to indicate that is our final answer. So place that in a big enclosed area there. Thank you for joining for this consideration of how to tell whether or not a function is differentiable at a specific x value. So I'll let you go work on your functions, see if they're differentiable at your x values. Thank you for joining. See you soon.